Hello, welcome to Guidancee Education Channel. We are continuing Class 11 Chemistry, Chapter 2, Structure of Atom. We will see the topic, Quantum Mechanical Model, Part 2, Quantum Numbers. This video will be slightly longer than the usual video because this is a very important topic and needs a little bit of more explanation. So, watch the video completely without skipping. And if you think the video is useful, consider subscribing my channel. Like the video, share the video with your friends who may also be benefited, and also give me your feedbacks as comments in the comment box. Thank you very much. Let us start the class. Our topic is quantum numbers. As per quantum mechanics, quantum numbers gives the energy level and probable location of electrons in an atom. As per Bohr atomic model, which is based on principles of classical physics, electrons revolve around the nucleus in paths called shell. The first shell can accommodate 2 electrons, the second shell can accommodate 8 electrons, and so on. I will show here 2 such paths of shell. Remember, classical physics does not take into account the wave nature of electrons. Electron, which has mass, is associated with the wave function. We have seen that solution of Schrödinger equation helps to calculate the wave function of the electron in its shell or orbit. His equation is the backbone of quantum mechanics. According to this concept, electron moves around the nucleus in three-dimensional space in a wave-like pattern. I have marked the nucleus and electron in the two diagrams. In three-dimensional space means you have to consider a spherical surface on which the electron is moving. Something similar to the surface of a ball or a sphere. This surface is at a distance from the nucleus. Schrödinger equation, which is a very complex equation, is written as H cap psi is equal to E psi. We know that H cap is a mathematical operator. It is really called Hamiltonian operator. Solution of Schrödinger equation gives the energy and probability of finding the location of the electron. The energy is quantized. This equation is Schrödinger equation. I will just note it there. In order to understand or calculate the quantum numbers, Schrödinger solved his equation for hydrogen atom or hydrogen atom-like species, that is, those species with only one electron. It was found that the same electron can have several energy levels. These energy states were named as one, principal quantum number, second one, azimuthal quantum number, and third one, magnetic quantum number. These are all the possible energy states the same electron can have. We know the single electron in hydrogen atom is in the first shell, but the wave function suggests that it can have a number of energy states. In addition to revolving around the nucleus, each electron spins about its axis, which gives rise to spin quantum number. Solution of Schrödinger equation for hydrogen atom gave absolute values for all these quantum numbers. For hydrogen atom, the energy levels depend upon only the principal quantum number. This could also explain two important phenomena, namely Zeeman effect and Stark effect of hydrogen spectrum, which Bohr atomic model could not explain. Now let us see what happened when Schrödinger equation was applied to multi-electron atoms. When Schrödinger equation was applied to multi-electron atoms, it was observed that absolute values could not be obtained for these various quantum numbers. What was the reason behind this? It was observed that energy level in the case of multi-electron atoms depended on two features. One is principal quantum number, that is where the electron is present, and also the charge on the nucleus, that is number of protons in the nucleus. We have already seen that for hydrogen atom there is only one shell and there is only one proton in its nucleus with one electron in its shell. But for multi-electron atoms there are a number of shells and also a number of protons in its nucleus. So the values obtained for the various energy levels in the case of multi-electron atoms did not agree with what was obtained for hydrogen atom. So this was solved by using the principle of approximation. So this method can give only approximate values, not absolute values. But later on, using advanced computerized techniques, it was observed that the energy levels obtained for multi-electron atoms agreed in principle with those for hydrogen atom. Therefore, the various quantum numbers obtained for hydrogen is also used for multi-electron atoms. Now let us understand these various quantum numbers. The location of each electron in the atom is identified or specified by 3 or say 4 quantum numbers. We will see them one by one. The first one is principal quantum number. We shall represent it as PQN, short form, also known as shell. You are familiar with this term from your smaller classes. This term shell is as per classical physics, which does not take into account the wave nature of electrons, represented by the symbol or letter small n. N is differentiated by numbers or known by numbers. N is equal to 1, 2, 3, 4, 5, and so on. These numbers are also allotted certain letters K, L, M, N, O, and so on. Each principal quantum number includes a certain number of sub-energy levels or sub-shell levels called azimuthal quantum number. Let the short form be AQN. Each principal quantum number, that is 1, 2, 3, 4, 5, etc. Each one of these will have a definite number of azimuthal quantum number, that is subshell or sub-energy level, and are represented by the symbol or letter small l. N stands for principal quantum number. L stands for azimuthal quantum number under each principal quantum number. The total number of azimuthal quantum numbers, that is the subshells which is admissible for each principal quantum number, is equal to 0 to n minus 1, where n is the number of the principal quantum number. Let us take the example of n is equal to 2, that is L shell. In this case, how many azimuthal quantum numbers are possible? First one is 0, then n minus 1. That becomes 2 minus 1 equal to 1. So, for n is equal to 2, azimuthal quantum number maximum is 2. Similarly, let us see for n is equal to 3, it will be 0 to n minus 1 means 3 minus 1, that is 2. 0, 1, 2. I hope it is clear. So, in short, we may say the maximum number of azimuthal quantum numbers for a particular principal quantum number is equal to the number of the principal quantum number. For n is equal to 2, there are two azimuthal quantum numbers. Remember, the numbering of the azimuthal quantum number starts from 0. Similarly, for principal quantum number 3, there are 3 azimuthal quantum numbers and so on. So, as the number of the principal quantum number increases, the number of azimuthal quantum number also will increase. So, they will be numbered as 0 to 1, 2, 3, 4, 5, and so on. For the first quantum number, there is only one azimuthal quantum number and it is numbered as 0. For the second principal quantum number, there are two, 0 and 1. For the third quantum number, there are three, 0, 1, 2, and so on. This type of numbering, excepting 0, is present for the principal quantum number also. So, to avoid confusion, they are allotted certain letters as S, P, D, F, G, H, and so on. So remember, the total number of subshells for any principal quantum number is from 0 to n minus 1. Third one, magnetic quantum number. We will represent it as M, Q, N. Magnetic quantum number speaks about the orientation of the azimuthal quantum number. That is, in which direction these azimuthal quantum numbers, that is sub-energy levels or subshells, are oriented. These various orientations of the azimuthal quantum number are also called orbitals. It is the direction in which the electrons are revolving round the nucleus. Orientation is best explained on the basis of the three coordinates, namely the horizontal one, the x-axis, the vertical one, the y-axis, and in between these two, the z-axis. All the three being mutually perpendicular, that is, orthogonal coordinates. In between these three, other directions are also possible. We will discuss all that soon. The nucleus is supposed to be in the center where these three coordinates intersect or meet. Magnetic quantum number is represented by the letter ML. L stands for azimuthal quantum number. For a given value of L, that is azimuthal quantum number, the possible magnetic quantum numbers are negative L to positive L, including 0. Let us take the example of L is equal to 2. How is L numbered? 0, 1, 2, 3, etc. and represented by the letter S, P, D, F, etc. So 2 represents D subshell. Okay. Now let us do the numbering. Negative 2, negative 1, 0, positive 1, positive 2. These are the possible orientations for D subshell. A total number of 5. In this diagram, I have shown only 3. We will know more about it later on. Now let us see the significance of magnetic quantum number or its importance or what information it is providing. It helps to explain Stark effect and Zeeman effect, which Bohr atomic model could not explain with reference to hydrogen spectrum. What is the reason for the motion of these electrons in the orbitals, which we call magnetic quantum number? Movement of the electron in the principal quantum number, that is the orbit or shell, is called orbital motion. Due to this orbital motion of the electron, an electric field is generated, and this electric field generates a magnetic field which causes the electrons to move in definite orientation. Now we will pass on to the fourth quantum number, namely spin quantum number SQN. This quantum number is represented as ms. Recall the magnetic quantum number for L is equal to 2. It has 5 orientations. There are 2 electrons each in each of these orientations, that is orbitals. Each electron spins about its own axis in addition to the orbital motion. This spin motion is explained by spin quantum number. The two possible spins are clockwise and anti-clockwise. That is, the electron may spin in the clockwise direction or in the anti-clockwise direction. The two directions of the spin are represented as plus half and minus half. If this is the orbital, this is one of the electrons and this is the other electron. Suppose this electron spins in clockwise direction in addition to going round the nucleus in the center. Then the other electron spins in the anti-clockwise direction. Significance of spin quantum number is that it helps to explain the magnetic property of materials. That is, if the orbital is fully filled, that is, it has both electrons, then the two spins in the clockwise and anti-clockwise direction will get cancelled and it will not show magnetic property. But if it is half filled, that is, there is only one electron, then it will show magnetic property. I hope this video was of great use to you. If so, like the video, share the video with your friends who may also be benefited, and also give me your feedbacks as comments in the comment box below. It is very important. If you have not yet subscribed my channel, do subscribe it now and also press the bell button for more videos like this. Thank you very much. In the next video, we will discuss how to calculate the various quantum numbers for each principal quantum number. Bye for the present.